We're going to go ahead and end out chapter 10, which is estimating means with confidence. And we're going to look at those difference in means. So again, we're following the same stuff we've been doing with confidence intervals and all that with proportions, but now we're just doing it with means. So we're going to determine whether we have those three conditions that are met. We're going to construct and interpret a confidence level for a difference, or a confidence interval for a difference between two means. And we're going to look at something called paired data sets and look at confidence intervals for the mean difference. So we have a difference between two means, but then we also have a mean difference. And we'll talk about what makes those different. All right, so we still have our three conditions. The first one is random. If we're doing a difference of means, then we need two random samples or two groups in a randomized experiment, so still needs to be random. We want each of those sample sizes to be less than 10% of each of the populations. And for normal large sample, remember we have three options when we're talking about means. We can either have sample sizes that are large or greater than 30. We can know that the population distributions are normal, or if they're less than 30, we can graph the data in our sample and see that we have no strong skewness or outliers, and we're still good to go. So let's check those conditions for a difference of means. A college student wants to compare the cost of 1 and 2 bedroom apartments near campus. She collects the following data on monthly rents in dollars for a random sample of 10 apartments of each type. Let mu1 be the true mean monthly rent for all 1 bedroom apartments near campus, and mu2 equal the true mean monthly rent for all 2 bedroom apartments near campus. Check if the conditions for calculating a confidence interval for mu1 minus mu2 are met. So we have our data still. Remember that first condition is random. So are these from two random samples? Yes, they are. We have independent random samples of 10 one-bedroom apartments and 10 two-bedroom apartments near the campus. So we're good to go. Our next condition is that 10% condition. So is our sample size less than 10% of the population? Absolutely, we can assume that 10 is less than 10% of all one-bedroom apartments and 10 is less than 10% of all two-bedroom apartments. And then that last one, normal large sample, we have a small sample size, so we need to make a dot plot of those rents. So when we do that, we see we don't have any strong skewness, and we don't really have any outliers in these situations either. So we're good to go. We can use the normal or large sample case. So remember our basic formula for constructing those confidence intervals is we take our statistics, that's that sample value that we're looking at, plus or minus that critical value, so either Z star or T star, times the standard deviation of the statistic or the standard error. And so when we do that, now this time we're doing a difference of means, so we're going to subtract those sample means instead. And when we do the standard deviation of the sample means, we remember we add them under the square root, but we don't know sigma, so we're going to, instead of using the population standard deviation, we're going to go ahead and use the sample standard deviation that's given to us. Don't always know the population, and that's called our standard error because it's a standard deviation of the statistic. So now we have x bar minus x bar for our statistic, and then we're going to have this whole equation plugged in for our standard error, and then we're still going to be using t star because we're talking about means. So this is our final equation then for constructing our interval. Alrighty, let's take a look at an example of a two-sample t-interval. So remember when we're talking about those inference methods in the plan, we're now on a two-sample because we're doing the difference between one mean and another mean. So this is what we would put for that inference method, a two-sample t-interval for mu1 minus mu2. The Wade Tract Preserve in Georgia is an old-growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 trees from each half and measured the diameter at breast height in centimeters. Here are summary statistics and comparative box plots of the data. So we've got our box plots comparing from the north and the south. And then they also gave us our sample sizes, our means, and our standard deviations of those samples. So how nifty for us. We have all that information. Part A says, based on the graph and numerical summaries, write a few sentences comparing the sizes of longleaf pine trees in the two halves of the forest. So we're just going to be using our distribution, talking about shape, center, and variability. So what can you say about the shape of each of them, the center of each of them, and the variability of each of those? We can start with shape. The distribution of DVH in the northern sample appears skewed to the right, while the distribution of DVH in the southern sample appears skewed to the left. We definitely have different tails, and there are no outliers in either sample, so shape is covered. How about our center and variability? Center, it appears that the trees in the southern half of the forest have larger diameters, so we have that larger mean. Remember, we were measuring the diameters. The mean and median for the southern sample are much larger than the values in the northern sample. And our variability, there's more variability in the northern pines. We have a higher standard deviation. The range, IQR, and standard deviation are all larger for the northern sample. So the range and the IQR is coming from our box plot. Remember, IQR is the quartiles, which are the edges of the boxes. So you subtract the two edges of the boxes. And then our range is the edge of the entire plot, those max and those mins. So just analyzing how we already know how to describe distributions. We're just using common sense for this one to talk about the difference. Now we're going to go ahead and do a confidence interval to talk about the difference between the means. So we're going to construct a 90% confidence interval. So we still have our four pieces of a confidence interval: state, plan, do, conclude. So we're going to go ahead and do the state portion first. We're looking for a 90% confidence interval for mu1 minus mu2, where, and then remember you define your parameters. So mu1 is going to be the true mean DVH of all trees in the southern half of the forest, and mu2 is going to be in the northern half of the forest. We're going to plan a 2-sample t interval for mu1 minus mu2. That's our inference method. We have random samples, so we're good to go. 30 is less than 10% of all the trees in the forest, and we have large sample size. 30 is greater than 30, so or greater than or equal to 30, so we're good to go. So all three conditions met, inference method stated. So now we're going to do the do section. So we have our two means, we have our two standard deviations, we have our two sample sizes. So we're going to go ahead and plug things in. You can use a calculator function, which we'll talk about in class, to get the confidence interval, and then you just state what your degrees of freedom is. You can also just do this with the whole formula as well. So if we use the formula, we subtract our two means. Our t value using table B is going to be 1.699. You can also still use technology for your table value. Degrees of freedom is 29. And then plug in those standard deviations squared. So we're going to conduct the standard error, times it by our critical value, which gives us 7. And then when we subtract our two means, we have 10.83. Add and subtract those to get our minimum value for our interval and our higher value for our interval. And then that conclude, we are 90% confident that the interval from 3.9362 to 17.724 centimeters captures mu1 minus mu2, which equals the difference in the true mean DVH of all the southern trees and the true mean DVH of all the northern trees. So notice the true is still with the mean because we're still looking at means here. So we're still taking a difference, but it's between the true means. So we still have that true value in there. So literally same thing, except extra work because we have to subtract. And that's why we're going to talk about that calculator function as well tomorrow in class. All right, so before we left for the break, we looked at 11.1. We're talking about testing claims about means. And that was just when we have one mean. We're going to go ahead and look at a difference in means today. So we're going to do those significance tests, looking at stating the appropriate hypotheses, performing significance tests, looking at how to find p-values, and we're also going to compare the difference between paired t procedures and two-sample t procedures. So we're going to go back to that paired data that we talked about last chapter. All right, before we do that, let's kind of recap significance tests just in general. We did do this before we left and a couple chapters ago. So let's look at the hypotheses first. So the first thing to remember is how we denote it. A null hypothesis is H sub 0. An alternative hypothesis is H sub A. Then we put our two colons, and then we put either P or mu, depending on if we're talking about a proportion or a mean. And then if it's a two sample, we would be doing a P1 minus P2 or a mu1 minus mu2. All right, so that's our notation. So then we just have to look at like what goes after those values, right? So if we're doing a one sample, it's just going to equal the parameter. So P equals 0.25 or mu equals 12. If it's a two sample, then we're saying it equals 0 because we're trying to show that there is or isn't a difference. If there's a difference between two things, then when I subtract them, I get 0. Our alternative hypothesis for a one sample and a two sample is going to be greater than, less than, or not equal to either the parameter if it's a one sample or to 0 if it's a two sample. So this should have also said greater than, less than, and not equal to. So it's all three of those still. So the only difference is a one sample is looking at a specific, like a different kind of number, whatever number is given to us, the parameter value. And a two sample is always looking at 0 because we're trying to show if there's a difference or not. Then we also had significance level alpha, right? So there are only ever going to be three values for that, 0.1, 0.05, or 0.01. And if it's not given to us, we're going to always assume 0.05. We're going to solve for p-value, so we're going to find the test statistic, we're going to find that t-value, and then either use the table or the calculator to find p-value. If we're using calculator, we're using two-sample t-test. That's what we'll be using today. If it's a one sample, we use a one-sample t-test, but that's that calculator function that we're looking for. And then the p-value, let's actually kind of remember what it actually is. A p-value is a probability of getting evidence for the alternative hypothesis, and we're comparing how strong it is compared to the observed evidence when the null is true. So if we assume the null is true, our p-value is telling us our evidence for our alternative. And then remember in our conclusion, we'll be either rejecting or failing to reject the null. If the p-value is greater than alpha, we reject the null. There is convincing evidence for the alternative. If the p-value is greater than alpha, then we fail to reject the null. There is not convincing evidence for the alternative. Remember to include your context. Don't just say for the alternative hypothesis, state what those hypotheses are. All right, so we're going to go ahead and start with a difference of means or a difference between means. So trying to show that our null hypothesis that they are the same, meaning that the difference is equal to 0. So that's going to always be our null hypothesis. We have three conditions to check for. So is it random? Does the 10% match for both sample sizes and populations? And then normal, large sample. Remember, we have three different ways of checking this one now when we're talking about means. Either for each sample, the population distribution is normal, or each sample size is greater than 30, or if it's less than 30, then we draw a graph and we see if there's any strong skewedness or outliers. All right, so let's go ahead and state the hypotheses and check conditions. So let's just make sure we know how to set up. Basically, we're doing the state and the plan section of our four-part big FRQ. Has the mean number of hours Americans work in a week changed? One of the questions on the General Social Survey asked respondents how many hours they work each week. Responses from random samples of employed Americans were recorded for 1975 and 2014, and they're summarized below. Do these data give convincing evidence at the alpha equals 0.05 significance level of a difference in the true mean number of work hours per week? So pay attention to this first part because that's going to be really important for part A. It's asking, does it provide convincing evidence that there is a difference? Okay, so that's our key thing. A, and we state our hypotheses. If I want to know, is there a difference, that means that my alternative is going to be when I subtract them, I don't get 0. It's not equal to 0. Because if there's a difference between these two numbers, I will get some sort of value. When I use greater than or less than 0 is if it tells me whether one of these is more or less than the other, right? So in this case, if 2014 was more than 1975, if that was what they were trying to ask, then we would be doing greater than 0, because if this value is greater than this value, I get a positive number when I subtract, right? If it said, is 1975 more, then I would be using less than 0, because that would mean that this number is greater, meaning that when I subtract these two, I get a negative number, which is less than 0. So if it asks, is there a difference, we just go for not equal to, because we're trying to show that it's not 0. But if they're trying to compare, if this question asks more specifically a comparison, think about, will it yield a positive number or will it yield a negative number? And that's going to tell you whether we have greater than or less than. And then we define our parameters of interest. This one defined them backwards, but same gist. You're literally just writing equals the true mean hours worked per week, and then just make sure you label the right one, right? So our mu1 in this case, or mu 2014, is the amount that they worked in 2014, and then mu 1975 is the amount they worked in 1975. Don't have to use 2014 and 1975. You could have used 1 and 2 like it did, but they have it labeled incorrectly there. Part B, check if the conditions are met. So is it random? Yes. Remember, you can't just say yes. You need to say independent random samples of 764 working Americans in 1975. It's coming from up here, right? So state how much is happening for each one. Be specific. Don't just say, yes, it's random, right? State that random sample. 10%, yes, it worked out for this one. 764 is less than 10% of all working Americans, and 1501 is less than 10% of all working Americans. And then does it meet the normal large sample size? Yes, both those sample sizes are greater than 30, so we're good to go. All right, so let's go ahead and calculate or perform that whole statistic or the significance test. So to do that first, we're going to have to find the t-value. So our formula is always the statistic minus the parameter or that value that we're studying over the standard deviation. So we have to use different formulas depending on what we're studying. My statistic for this one is going to be mu1 or x bar 1 minus x bar 2, because I have two different means. And then my standard deviation is the standard deviation equation for when I solve an x bar 1 minus x bar 2. Then we can, when we're calculating things and using degrees of freedom, we can use either technology. So remember, technology, we're going to be doing a 2-sample t-test. Or if you're using the table, which is option 2, take the smaller sample size and use that for your degrees of freedom. All right, so let's go ahead and put it all together here. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy men who volunteered to take part in the experiment. They were randomly assigned to two groups. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. Remember, double-blind means that the people being studied and the people conducting the experiment or studying the results don't know who has who. So the participants didn't know whether they were taking calcium or the placebo, and the people who were recording their results also didn't know whether they had taken calcium or placebo. The response variable is the decrease in systolic blood pressure for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative number, so here's the data. So we have our information there. Alrighty, do the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo on average for subjects like the ones in this study? All right, so before we start our state plan do conclude, here's what we're looking for. Does it show that a calcium supplement reduce blood pressure more than a placebo, right? So that's what we're studying. So we're looking at if calcium is greater than the placebo. So if we're going to write our hypothesis as calcium minus placebo, then I want it to be greater than 0, right? If I write it as placebo minus calcium, then I want it to be, I want it to be less than 0. So it just depends on how we're going to state those hypotheses. But we're probably going to go with calcium minus placebo here just because we usually just do group 1 minus group 2. All right, so let's go ahead and do calcium minus placebo. Go ahead and state those hypotheses. What are your hypotheses going to look like? All right, so in our state portion, you should have had your null hypothesis equaling 0, and then your alternative hypothesis, again, if we were doing calcium minus placebo, being greater than 0, okay? You can do mu1 minus mu2, that's fine. Just make sure you label them. So mu sub c is the true mean decrease in systolic blood pressure for healthy men like the ones in this study who take a calcium supplement. Remember to define your parameter as much as possible. Alrighty, and then we also need to state our alpha when we're doing a significance test. They didn't give us one, so we're going to use alpha equals 0.05. All right, so next section is plan. Do all three of our conditions met? And state our inference method. So we have a 2-sample t-test for mu1 minus mu2. Is it random? The 21 subjects were randomly assigned to the calcium or placebo treatments, so we're good to go. Is there a normal large sample? The sample sizes are small, but the dot plots show no strong skewedness and no outliers, so we have to actually draw those out. All right, so note on this one too that we didn't check 10% condition, okay? So 10% condition only happens if we're pulling people from a population, right? But we're not pulling from a population. Technically we are, but we're not comparing it from a population, right? We are doing a study that's focused on these people. So because we just have that 21 in there, we don't need to check the 10% condition because it's not being pulled from a larger population. We have a very focused study. Alrighty, so our next section is the do section. So we've got to list out everything. So the first thing we have to do, in this case, they didn't give us the mean or standard deviation, right? So the easiest way is to type everything into the calculator, especially for your standard deviation, because you don't want to actually solve for standard deviation. Remember, to solve for it by hand, you have to find the mean, then you have to subtract all of the values from the mean, square those, add them up, it's a whole big process. So just type each of these into your calculator, list 1 and list 2, and then do the, I'm pretty sure it's second vars, or maybe it's stats calc, and then we have the 1 var stats because we just have the one list, all right? Or you could do 2 var if you put them both into the list at the same time. But either way, your calculator will give you your mean for each value, your standard deviation for each value, and then you want to also write your sample sizes for each value, okay? So make sure we're listing them all out in your do section. Then we're going to calculate t, which is x bar 1 minus x bar 2, so subtracting those two values, and then we subtract 0 minus the parameter, statistic minus parameter, plug it into our standard deviation formula, so standard deviation squared over sample size, standard deviation squared over sample size, add that square root, and we get 1.604 for our t value. So not done yet. That's just listing out these parts, right? Then we have to plug it into the calculator to find p-value. So if we go to 2-sample t-test, that gives us a p-value of 0.0644 using degrees of freedom 15.59. Remember, your calculator gives you a different degrees of freedom, so make sure you state what it said. That way they know that you used the right thing in your calculator. All right, so we've calculated our p-value. That's the important part because we now compare it to alpha in our conclusion. So are we going to fail to reject, or are we going to reject the null hypothesis for this one? Because p-value is greater than alpha, we fail to reject h sub 0.
The experiment does not provide convincing evidence that the true mean decrease in systolic blood pressure is higher for men like those who take calcium than for men like these who take a placebo. So remember, we go back to what our alternative was. We're saying there is not convincing evidence for the alternative, and our alternative was saying that C minus P is greater than 0. We are trying to say that calcium is more than the placebo. So that's what we're going to put in our context, right? So we're saying that the decrease is not higher, there's not convincing evidence that the decrease is higher for those who take calcium than for those who take the placebo. Alrighty, and sometimes we'll get a question that says interpret the p-value. So interpreting the p-value is assuming the null is true. There is a blank probability, so your p-value, probability of getting a difference, calcium minus placebo, in mean blood pressure reduction for the two groups of 5.273 or greater, just by chance involved in the random sample or random assignment.